Hey everyone, here's just a little bit more explanation of some of the homework problems from 11-4. With these first 6 problems, I was saying in the video that these are really straightforward, and yet I could imagine that they might not have been so for some of you if you are still not beginning each problem by writing down one of the 2 formulas. I find for some students, it takes them a long time to get to the place where they understand that writing down a formula is work. It is a step towards solving the problem. And it just takes them a while to get used to that. But notice in every single one of these problems where I've written up the solutions here, I started by writing down the formula. So in problem number 1, here I wrote down this version of the formula, and then I started looking for ways to plug information from the problem into the formula. In the second problem, I wrote down this version of the formula. And again, it doesn't matter which version of the formula you write down, but sometimes if you choose one version over another, you might end up having to do a little bit more algebra. So if you're nervous about your ability to do the algebra, you might want to try to get better at choosing the formula that will require less algebra of you. And yet the catch-22 is that in order to make the better choice, you probably have to know something about algebra to begin with. In any case, look at problem number 3 here. I wrote down the formula. Problem number 4, I wrote down the formula. Problem numbers 5 and 6 also. I mean, it may not look like this is what I began with, okay? In the middle of all this, it's kind of in the middle of all this work. But that's really the starting point for my work, is the formula. And now, where does stuff come from to plug into that formula? Okay? Let's move on to the other problems, which I imagine might have given a lot more people a lot more trouble. Excuse me, number 7, part A, really I have no comment on that. That should have been really straightforward. Part B, all of the steps that I'm doing here, I can't give you like a formulaic approach, a step-by-step, do this, do that, do the other thing to solving a problem like part B. This is what people like to commonly refer to as a word problem. I like to refer to it as applied arithmetic. Okay, everybody can do 7 plus 8 if you ask them to do 7 plus 8. Everybody can do 50 divided by 10 if you ask them to do 50 divided by 10. But you give them a problem where they have to decide what things to multiply, add, or divide. Now all of a sudden they're lost, right? But it's just making the decisions to apply your knowledge of arithmetic to solving a problem. So I don't have anything else to say about part B. I think what I'm doing here is pretty self-explanatory. I will say this, instead of converting the feet to inches and finding out that, all right, the total route for my daughter driving her bicycle from our driveway to the neighbor's driveway and back is 1,800 inches. Instead of going that route, we could have converted the inches in the tire's circumference to feet, right? Divide that by 12, and you're going to get about 3.35 feet approximately. I'm doing the arithmetic in my head and I'm estimating there. About 3.35 feet for the circumference. And so then if you divide, instead of 1,800 inches of travel time by 40.8 inches per tire circumference, if you divide 150 feet of travel distance by 3.35 feet of tire circumference, you're going to get the same answer, about 44 revolutions. And that would have been a perfectly fine way to do this problem also. This one here, you might help me to explain a little bit about. All right, you've got this inner tube. I don't know how many of you have ever seen an inner tube folded up into a box, but like all the air is taken out of it, right? And then it just gets kind of folded up and packed up into a box. So when you take this inner tube out, again, before you put any air in it, it's just this, floppy thing like this, right? But then when you put air in it, then its shape becomes circular. But here's the thing. The distance around this inner tube when it is in circular form is not going to be any different than the distance through this tube when it's in this sort of wiggly wobbly form, which is not going to be any different from the distance through this tube when it's in the packed up form in the box. So pick a point in the tube and start traveling, right, from here to here. If this is a square box, which is 3 inches on each side, then that is approximately 3 inches of distance through the tube. Okay? And now here's another 3 inches of distance through the tube. I know it's not exactly 3 because you've got this little bit of room over here, right? But we're just asking for an approximate answer here. And so here's another 3 inches of distance through the tube. And, I identified all the 3-inch lengths. There's 11 of them. So the distance from this point in the tube, wiggling through the tube, and then finally all the way back to where we started would be 11 threes or 33 inches of circumference. That's what I'm doing here. That's kind of the thinking about where this is coming from. And then once you have the circumference, finding the diameter is super easy, okay? Number 9, a word about this. It says a string wraps exactly once around circle A. So here, I've drawn the string in red here, okay? Now, exactly once, which means it actually comes back together at the top. It meets itself at the top. But I just put a little gap there so that it maybe communicates more the idea of a piece of string. If I just made that solid, you wouldn't be thinking of it as a string. You'd just be thinking of it as the circle. So here's the string. Or, maybe it was all connected at one point and I just snipped it and now it's beginning to fall off of the circle. And I take that piece of string, that same string, whose circumference or whose length I calculated to be 18 pi. And I wrap that string around the bigger circle. Now, if it's a bigger circle, the string's not going to go all the way around it, right? I don't know how far around. I didn't know when I was working through this problem if that piece of string from circle A would go more than halfway around the circle or maybe less than halfway around the circle. I didn't know, but it didn't matter that I didn't know exactly how much, because that's the problem, is trying to find out how much. The picture doesn't have to be perfect here. It only has to be good enough to help me solve the problem. Right? So here's that string going from 12 o'clock, and I'm just guessing to somewhere around 7 or 8 o'clock down there. And then here's the theta, or the angle, or the number of degrees around the circle that I'm trying to find. Well, that string that was 18 pi centimeters long over here is still 18 pi centimeters when I wrap it around the other circle. But now that 18 pi centimeters isn't a circumference on this circle, it's an arc length, right? The circumference of this circle is going to be 28 pi. I've shown that calculation up here. So plug the 18 pi in, the 28 pi, multiply both sides by 360 to solve for theta, and you're done, okay? But the key here was calculating the length of that string from the first circle and then transferring that same length of string over to the other circle where it becomes an arc length. I hope that makes sense, okay? Number 10, I did in a slightly abstract fashion. And what I mean by that is, notice I did not give any measures in this problem at all. No radii, no diameter, no circumferences, no angles, no nothing. I didn't give any particular measures. And I solved the problem also by not using any specific numbers or measures. That's what I mean by solving the problem in an abstract fashion. But think about this. The fact that I did not say that this problem had to be about a circle of any specific diameter suggests that it probably doesn't matter what the diameter is for this problem, and therefore you could just make up any diameter that you want. And instead of solving the problem kind of abstractly like I did, solve it a little more concretely, that is, for your particular circle with your particular diameter. In fact, let me show that right now. Let's just choose a diameter for a circle. And instead of calling it just, D, like I did in my picture, let's call it 10 centimeters for the diameter, or 10 inches, or whatever, okay? And so we've got a 10-inch diameter circle, and now we want an arc whose length is equal to that diameter. So we want an arc that is going to be 10 inches long. And again, I don't know exactly how far it goes. The picture doesn't have to be perfect. It just has to be good enough. For sure, that arc is not going to go halfway around the circle, because the path from point A to point B around the circle is certainly going to be longer than the path from point A straight down to point B, right? So there's no way is that arc going to go 180 degrees around the circle. Okay? And now here's the center of the circle. My pen turned off on me again, as it frequently does. Let's put the center of the circle in there. Oh, come on, pen. There we go. Put the center of the circle in there. The question is, what is that angle measure? Well, we've got an arc length. We've got a diameter, which means we could get a circumference. So those are 2 out of the 3 variables in that arc length formula. And again, here's one version of the arc length formula. Arc length over circumference. That's part of the length. That's the whole length around, equals the theta, which is part of the degrees around a circle, over the whole number of degrees around. Now let's plug values in. The arc length is 10. Right? What is the circumference? It's the diameter times pi. 10 pi equals theta over 360. Now to solve this for theta, multiply both sides by 360. Now look, before you even pick up a calculator, aren't these 10s going to cancel out just like my d's canceled out up here? See, it doesn't matter what number you pick for d, it's going to cancel out right here, which is what the algebra or the abstract solution shows us up here. No matter what you choose for the diameter, it's going to cancel itself out in the circumference, right? So that cancels out there. Your theta equals 360 times 1 over pi, or 360 divided by pi. Okay? Well, if you watch this, I hope some of that was helpful and gave you a more confident feeling about how I'm doing the solutions to these problems. Okay? See you soon. Bye.